we're here, right? We understood that it is 3 parameters, and here is the explanation of our calling convention. As you remember, the mem set is going to receive 3 parameters, but the function, the fast calling convention is saying it's going to push the parameters into the stack in reverse order. In other words, the first parameter being pushed is going to be size t, the second one is going to be integer, the third one is going to be the destination buffer. You can see that here right there. If we see the pushes, those are pushing the parameters into the function. Since, as you know, the first function to be executed is going to be sub ESP78, and then the push is going to be 44, and you can see that IDA is smart to recognize that that is the size t, which is the last parameter being pushed into the stack. That's the last parameter being pushed first, then the second parameter, the integer, and then the final parameter, the destination. You see that those are being pushed in reverse order. After that, it's going to call memset. Okay, let's see in real action in the debugger how this works, because it is also important that after we call memset, the result is going to be stored into a specific it's going to be stored it's going to return the address of the destination buffer. And here is the second thing, guys. Everything that is returned is going to be returned into the EAX register. In other words, every time you execute a Windows API, you will see that you will need to check the EAX, which is going to have the result and the return value. So we come here to the debugger. Let's start executing it with F7. We click F7, then we're gonna be ready to start pushing into the stack. You can see here in the stack, in the lower right side, this is the stack. As soon as we push the 44, it's gonna show up here. Okay, so let's see that 44, you see, and then there is another instruction which is important. LEA is load EAX. It's basically saying EAX, you need to point to a specific value in the stack. It's just gonna point to a specific variable. If we do that, we can see that EAX is now pointing to a specific address. Okay, that address, if you see after the push 0 is push EAX. In other words, that address that EAX just got is gonna be the first parameter, which is the destination buffer. We can in WinDebug, we can right click here in EAX and click on follow in dump, and then here in the lower left you can see that the address now is pointing to the same destination buffer. Another way to do that, you can quickly go to Immunity Debugger command prompt and do dd EAX, enter, and you will reach exactly the same address. Okay, guys, so here it is the destination buffer. Then it's gonna push the 0, which is the value to put into that buffer, and again check the stack and you will see how it is being pushed there. And finally it's gonna push EAX, which is the destination buffer. Now here, guys, if we do F8, which means don't step into the function but just execute everything, it's gonna clear all the different buffer with a size of 44 hexadecimal, or in other words 68 bytes. So let's do that. F8, and you see that everything was cleared, and EAX is pointing to the destination buffer. Okay, now guys, there is something very important that I want to explain you also. We saw that how the arguments are being pushed into the stack, and then we saw how we execute it, and the return value is in the EAX. But there is another important value, guys, which is the return address. Okay, let me explain you that. I'm gonna click on debugger, right click and say new origin here. This is a trick in the debugger where we can start executing again the instructions. Basically, we are saying to EIP, which is the one that has the instruction to be executed, point back to this address. That way, I can explain you again how we can do this, and it is very useful anytime you want to jump into a specific instruction. You can jump to a specific instruction and say to the debugger, start executing from here, if you wanna analyze something. Okay, so here I'm gonna do again the push F4, then we're gonna do the LAX, which we know it was that address, the push 0, push EAX. Okay guys, we are again here, and we have in the stack the 3 parameters ready. Now, once this memset function is executed, the program needs to return to the next instruction, which is this value, right, in D4 1011 address. So, but how the program knows that once it gets into the function, it will return here? So that's called the return address. It's going to help us with that. That means that once we get into the function in the call, if I press F7, the first thing that is going to happen is that the next instruction after the function is going to be pushed into the stack, so that once this function is done executing, it's going to know where it needs to jump back. So let's do that. I'm going to press F7 here in order to step into the function, and you will see here in the stack that the address D41011, which is the next instruction after the function, is going to be pushed into the stack. Let's check that. F7, you see that the instruction is in the stack, and then I just jumped into the memset, and here is going to be all the function related to the memset that, as I said before, you don't need to reverse it, you don't need to understand it, because it's just a standard function, right? And you can see, I mean, there are multiple functions. So I'm just going to go to the end of the function by saying debug execute till return. It is saying execute everything and stop right into the return just before getting out of the function. Okay, I execute, and we are here in the last instruction. The last instruction of every function is a return. That is telling go back where you were before executing. You can see that once everything executed, return is gonna execute, is gonna go to the stack, is gonna read wherever is the address there in order to jump back. As you can see, it is pointing to the instruction that was saved before stepping into the function. Once it is executed, it's gonna take this address and jump back where we were before executing. Let's do that. We click on F7, and you can see that we are just after the memset instruction. Okay guys, so that's very important for you to understand. So now we understood everything. We understood how the return address works, we understood how the parameters are being passed to the stack, and now let's start analyzing more code. As I said before, the best approach is to be switching between IDA and the debugger. In the debugger to confirm what we are seeing in the IDA Pro, but in the IDA Pro documented everything, and the debugger just confirming our findings. So let's go to IDA. We just passed the memset. Then it's going to do an XOR. Again, we can see here that it has some instructions, which is the spin color, get system info, and then eventually something recommended, guys, is you should go quickly and check all the different functions so that you have a better overview. So in this case, we can get the graph overview, and we can just go quickly up and down to see all of it. We can see that this is a very small function. Let me just move this guy to here. So we can see that it's a very small function, right? And in a real scenario, you will have multiple functions. You need to get into every specific function and do a quick pass through so you can have a better idea of what's going on. So here, for example, my recommendation is you click on call. When you click on call, all the calls being used in the function is going to be highlighted so you can see what are the main functions being executed. We can see here that all the calls are in pink color, which means it is just instructions calling Windows APIs. There is no custom code, which is the intention of this exercise. We can see that here there is a virtual alloc and here is a create process function. Virtual alloc is very important because it's going to allocate memory for the process, and create process is actually going to execute a program. Okay, so since we're just understanding Windows APIs, let's just quickly go to this one to see how the parameters are being passed again, and then to the create process, and we are done with this exercise. Okay, so we're gonna put a breakpoint in virtual alloc. Again, here you can see that IDA is gonna give you all the parameters just by putting your mouse over the function. Again, if you don't know what is virtual alloc, go to MSDN and it's gonna tell you what is there. Okay, so if we come here, we can see that the debugger was able to also understand virtual alloc. Sometimes it's not. That's why IDA can help us. So we go here, press F2, put a breakpoint there, and you know what? I'm gonna put a breakpoint in the first parameter. You can see that also Immunity Debugger is able to understand the parameters. So this protect, if we go to IDA and check the parameters, protect, you can see it is the last parameter. As expected, since it is the last and it is pushing the parameters in reverse order, this is going to be the first one. Then it's going to be FL allocation type, then W size, then LP address, in reverse order. So we can see here that it is the first one is push. I'm going to put a breakpoint here, and I'm going to click on play or F9 to run until that specific point. I just want to skip over all the other instructions, and here we're going to push the first value, F7. And now something important here, guys. It is pushing the number 4, but the number 4 in the context of virtual alloc means page read write. In other words, what do you want to do with that specific allocation? You want it to be read write with read write permissions. Okay, so we click F7, we can see that it is been pushing the stack. Then again, EAX is going to point to a specific buffer. Every time you see LEA instruction, it's like a pointer. Everything passed into the register is going to be an address always. So we click F7, we can see that EAX is pointing to that value. I always recommend that every time you have that specific buffers, you just put it in the memory with DDAEX. Oh, it is not pointing to anything. Let's see the reason. Okay, so even though it is expecting an address, that address is not ready yet, so we're going to skip over it. But the most important thing here, guys, is that that specific value is going to be calculated here, right? That's the reason we didn't get it. So let's see. We are going to see what's going on there. After that, it is a push. We saw it, 3000. Then there is a shift left, EX4. If you remember in the slides, shift left is like a multiplication. Okay, 2 to the power of 4. Okay, if we click F7, we can see that now EAX is pointing to a different value. Let's see that if this value is ready now. It is not allocated. When this value is not allocated, you won't find here the follow in dump option. In other words, that value is not in memory, and you can confirm here that if you do DDEAX, it is not pointing to anywhere, even though it's supposed to do that. But the reason is because even though the load EAX instruction expects an address, it is being used as a size. You can see here that the final value of EX is going to be used as a size. That's the reason we didn't find an address in that specific option. We click F7 to push it into the stack. It is there. Then we click on the address. That means what is going to be the address that you want to allocate in memory. If you push 0, that means null. That is telling the operating system, you choose the address. I don't care about the address. You give me the address, whatever you want. Okay? So we click F7, and you can see that now that we are ready to do the call, Immunity Debugger is giving us the nice display of all the parameters in the order. Even though we push them, as you remember, in reverse order, Immunity saying, okay, here is all the parameters in the right order, ready to execute. Once we execute this, again, where is going to be the return value, guys? In EAX, right? So EAX is supposed to have the address allocated. So let's click on F8 to step over. And you can see that now EAX is pointing to a specific address. We can go here and check it with DDEAX. And we can see that now we found that address in memory. Also again, with EAX, if you right click on it, since this is an allocatable address, we now found the follow in dump. If this is not a valid address, we won't see this follow in dump option being displayed. Okay? So this is just another example, guys, that you can see how we can push instructions, reverse order, and finally how we get the results in EAX. So finally, let's go to the final example, which is the create process. Create process is very interesting when doing malware analysis. If you see a malware calling create process, that means it's going to try to execute another binary. Normally, it will decode binary in memory, and eventually it's going to call create process to run it in order to run a second executable in the system. So I'm going to put a breakpoint in here, in LA. We press F2, we click on play, we are there, and then again LEA instruction, which is supposed to load an address into ECX. We see that ECX is pointing to this. We right click, following dump, we can see that that's a valid address, and we're gonna start pushing. You can see that again all the parameters Immunity Debugger, since it is a well-known API, it is able to understand them. So we just click start pressing F7. We start pushing all the parameters into the stack, and once we are just about to run, you can see that the last parameter pushed, which is the first parameter telling us the file name to be executed, it was pushed into the stack, and again when debugger is ready, giving us all the parameters. Once we execute this, what is going to happen is the calc is going to be pop up, and the return value is going to be, I think, a handle in EAX. So we click F7, and you can see that the calc get executed. In a real scenario, it's going to be a binary being running in your system. So that's pretty much all about Windows API calling convention, guys. Practice with these exercises, see how the functions are being pushed, play with the return address to know where you need to jump back, how the operating system knows where it will jump back after execution functions, and finally check the return value